So it's called permutations and combinations. Those are two sub-branches of combinatorics. They're very different from each other, but very related. And we start out with the fundamental counting principle. I'm going to tell you a little secret. In math, anytime someone says something is fundamental, that means it's really, really both basic but profound and important. So just for kicks, underline the word fundamental. That means it's important. In fact, technically, Mark, I could teach you this lesson and then throw the test for this unit at you, because you can do everything with today's lesson. And in fact, Kyle, whenever I get confused, this is going to be my fallback. Whenever I get to a tricky question, I almost always say, you know what, there might be a shortcut that works. I'm going to go with the fundamental counting principle instead. Here's our problem. It says this. Lucy is shopping for an SUV. The dealer says that she has 3 different models and that each model is available in 5 different colors. And what I'd like to know is, okay, how many different ways can Lucy buy a vehicle? We're going to start out with something called a tree diagram. A tree diagram says, okay, what are the different choices we can make? We can pick a model, and we can pick a color. So for your tree diagram, you would list the 3 models, and then from each one of them, you build a tree for the color. Eventually, we're going to break away from this because it's tedious. We're going to find a shortcut. But looking at this, without bothering to fill in these, can you tell me grand total, how many different outcomes are there? How many different ways can she buy a vehicle? Yeah. 15. Now you can get them by counting the branches at the end. There's 15 of them. Can you see a shortcut for finding 15 based on the fact that there's 3 models and 5 colors?
The different colors times the number of models.
And believe it or not, that's the fundamental counting principle. The fundamental counting principle says, you know what? If you're making choices at different stages and you want to find out the total number of outcomes, you multiply them. You multiply them. Which may not seem very profound, hugely profound, it turns out. So let's fill in the blank. Lucy has 15 choices. B says, look at the number of choices there are for the model and the number of choices there are for the color. Giancarlo has said, hey, Dueck, 3 times 5. The dealer tells Lucy that each of the sports utility vehicles comes in 2 editions. SE, standard, and LE, leather edition. It says, use a tree diagram to determine how many choices she now has. I'm already going to start to break away from the tree, Logan. Instead, I'm going to draw a blank. Dominic says, I'm good at drawing a blank. No, we mean we're going to be drawing a blank here in math. This is going to be one of the first toolbox tricks that I give you. Ready? I'm going to go like this. She can choose the addition, so underneath here, write a little addition. I'll do ED for addition. She can choose the model, and she can choose the color. In your homework, you don't have to write out the words. You could use letters like E, M, and C, or you could not put anything, but in our notes, so that I know what we did, we're going to fill this in. How many different additions are there? What does the question say? How many different additions are there?
2.
Put a 2 here. How many different models are there?
3.
How many different colors are there?
5.
Giancarlo, we're going to extend and generalize your fundamental counting principle. If you're making 3 different choices, you know what you do with all 3 numbers? You could draw the tree, but I don't want to draw 30 branches. Okay? Instead, I'm going to draw blanks for each choice. I'm good at drawing a blank. Next page over. I heard that. Okay. So, The fundamental counting principle. There should be like an echo, almost like a Darth Vader. The fundamental count. Thunder should roll in the background. There should be a lightning flash. This is really important, and it doesn't sound that profound. But again, we're going to build the next 5 or 6 lessons from this and get into some really cool stuff. For example, we'll learn that we can actually use this to figure out things like airline routes and stuff like that. It says, consider a task made up of several stages. The fundamental counting principle states that if the number of choices for the first stage is A choices, and the number of choices for the second stage is B choices, and the number of choices for the third stage is C choice, etc., you multiply them. The answer is going to be A times B times C times D times E times F, etc. So example 1 says, a toy manufacturer makes a wooden toy in 3 parts. Part 1, part 2, and part 3. It says, determine how many different colored toys can be produced using... I'm not a big fan of tree diagrams in this unit. I'm a huge fan of them in the probability unit, but not in this unit. So I'm going to cross that out. Instead, I'm going to fall back on the fundamental counting principle. It looks like there's 3 choices to be made. Choice 1, choice 2, choice 3. Part 1. How many choices do we have for part 1, the top part?
2.
And how many choices do we have for the middle part?
3.
And how many choices do we have for the last part? Is it that easy? Well, we're going to get tougher, but we're starting off with the fundamentals. How many different choices are there, grand total? No calculator. In your head, please. 12. 12. 12. I could have drawn a tree, and it would have been 2 branches, and each of those 2 branches would have had 3 branches, and each of those 3 sub-branches would have had 2 sub-sub-branches. Forget it. Okay. Pardon me? Well, it actually, for probability questions where you almost always only have 2 outcomes, a tree is very useful, but not as much for this. So, repeating myself. In the previous example, the toy, listen close, consisted of part 1 and part 2 and part 3. And we found the total number through multiplication. In fact, in this unit, the word and means multiply. The word and means multiply. Now that's different from English. In English, if I say, what's 5 and 6? What would you tell me?
30.
In this unit, it's 30. Normally, it's 11. Not in this unit. Both in combinatorics and in probability, and means times. And means times. So, a math quiz consists of 6 multiple choice questions. Each question has 4 choices. How many different sets of answers are possible? How many questions are there? How many blanks am I going to draw? How many questions are there? How many blanks am I going to draw? Draw 6 blanks. 1, 2, 3, 4, 5, 6. How many choices do I have for the first question? And how many choices do I have for the second question? And how many choices do I have for the third question? 4 and 4 and 4 and 4. Now you can go 4 times 4 times 4 times 4 times. Wait a minute. We have a lovely Math 9 shortcut that can write that way shorter. What is a better way to write that? Which is what? On your calculators. And you already see we've gone long past us being able to count these by hand and be successful in not missing any. Is it 16,192? That's a guess. What is it? 4 to the 6th? It's also 2 to the 12th. Sorry? 4,009. I was off. 4,096? Okay. That's the number of different answer keys. Or you know what? Suppose you're writing this test and you're randomly guessing. That's how many different ways there are of guessing the answers. Of those, how many are perfect? 1. If you're randomly guessing, the odds of you guessing perfect would be 1 out of 4,096. That's next unit, but study is the message I want to give you. Guessing on multiple choice questions doesn't work very well. Okay? There's 4,096 for only 4 questions. Sorry, for only 6 questions with 4 answers each, there's 4,096 different ways that I can create an answer key. Is it 4,096? I got people looking at frowning. Is it? Yeah, okay. And if you were guessing, only one of those is perfect. The odds of you guessing randomly and getting perfect, basically 1 in 4,100. Let's get a little trickier. What if I give you a restriction? Okay? Whenever they give me a restriction, no matter where that restriction appears in my blanks, I always deal with it first. Even if it's the last blank, I still deal with it first. If it's the first blank, I deal with it first. If it's a middle blank, I deal with it first. Let me show you what I mean. Eric has been assigned the task of determining how many odd 4-digit numbers there are. Underline the word odd. What's an odd number? A number that 2 doesn't go into. Can you rattle off some odd numbers?
7,
3, 1, 3. In fact, how can I tell that a 4-digit number is odd? Do I have to look at every single digit?
No, just the last one.
That's our restriction. And even though it appears last, we'll deal with it first. Now, I have to do one more thing. When I'm talking, Logan, about 4 digits, for this entire unit from now on, if I'm talking about a 4-digit number, it can't start with a 0. That would be a 3-digit number as far as I'm concerned. Okay, so I wrote down here, this is a 4-digit number, that's a 3-digit number. Okay? The first step of his work is shown. He drew 4 blanks. Why did he put a 5 in for the number of choices for the last digit? Underneath here, let's write 1, 3, 5, 7, 9. He's saying, you know what? It has to end in one of those. It has to end in one of those. Check. The second step, so now he's saying, okay, by the way, how many digits are there to pick from? Grand total. How many digits are there? 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. How many choices do I have for the first digit? What did I say we can't start with?
Can't start with a 0.
So where did that 9 there come from? No 0. I'll write, you can write 1, 2, 3, 4, 5, 6, 7, 8, or 9, or you can just say no 0. No 0. How many choices does he have for the second digit? Are there any restrictions on the second digit? So you know what? He's got, so we did this. 1, 2, 3, 4. We said he's got 5 choices for the last one because it has to end in an odd. He's got 9 choices for the first one because it can't begin with a 0. How many choices does he have for the second digit? How many digits are there, grand total? How many choices does he have for the third digit? How many digits are there, grand total? How many odd 4-digit numbers are there? I can do this in my head. 10 times 10 is 100. 9 times 5 is 45. It's 45 times 100. Please tell me the answer is 4,500. Is that right? Okay. B. Eric has now been assigned the task of determining how many odd 4-digit numbers there are that have, underline this please. Once you've used a number, you can't use it again. So here is the second tool I'm going to give you. The first tool is drawing a blank. I'm good at drawing a blank. First tool is drawing a blank. The second tool is the notion, how many of you have ever played Scrabble? Okay. I'd like you to imagine a grab bag with Scrabble tiles in it. And I kid you not, until I get good, I draw it. Over on the left here, there's my little grab bag, and I'm going to put 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Just kind of jumble them up. There's the Scrabble tiles. There's the digits from 0 to 1. Number 1 says, explain why the first step in A is still valid, but the second step... I'm just going to walk through the whole thing. How many digit numbers are we trying to create? How many blanks am I going to draw? What kind of a number am I trying to create? An odd number. What makes an odd number an odd number? What it ends with. What can it end with?
1, 5, 7.
How many choices do I have for that last number then? Put a 5 there. But now the problem is, once you've used up a number, you're not allowed to put it back in the bag and shake things up again. It stays out. So what I'm going to do then is I'm going to pretend that the number that I picked, oh heck, was a 9, as an example. Cross out the 9. How many numbers are left in my grab bag for my first choice now? Not 10. How many numbers are left in my grab bag for my first choice? 9. Oh, but what can't I use? So how many choices do I really have? 8. Let's cross out an example. Maybe it was a 2 that I put there. And this is why that little Scrabble bag helps you keep track of your choices along the way. How many choices do I have for my second digit now?
7.
Count carefully. 7's wrong.
8.
Why 8? Because what's back in play now? Ah, the 0's back in play, right? By the way, you're seeing it's really easy to make a sloppy mistake. The math is we're multiplying or we're adding, but it's very, very easy to make a sloppy mistake. I find the drawing a blank, the Scrabble bag helps me keep track, and it takes 1 second. It's good bang for my buck. So there's 8 left. Let's suppose I picked, let's pretend, Alyssa, I picked the 0. How many choices are left for my third digit? 7. If I'm not allowed to use the same number twice, how many 4-digit odd numbers are there? 8 times 8 times 7 times 5. Can I do that in my head? 8 times 8 is 64, times 5 is 320, times 7. Well, 300 times 7 would be 320 times 7. 2,140? No, 2,540? No, what is it? 2, I carried the 1 wrong. 2,240. Okay. So 2 says determine, there's the answer. This is where it's going to get a little trickier. Okay. This, by the way, I like this question. I like this question. I like this question. A classic, easy question for me to test the fundamental counting principle is to say, hey, how many odd 3-digit numbers are there? How many odd 5-digit numbers are there? How many odd 5-digit numbers are there if you're not allowed to repeat numbers? There's a great part A, part B, part C. License plates. Car number plates in an African country consist of a letter other than I or O, followed by 3 digits, the first of which cannot be 0, followed by any 2 letters which are not repeated. How many different car license plates? You know what? I'm drawing a blank. What are the choices along the way? It says they consist of a letter, except what can't I use? You know what? The way I show that I can't use something is I do that. That's a nice shorthand way. So, how many letters in the alphabet are there normally? How many choices do I have here? And followed by what? 3 blanks. Any restrictions on these?
No zero. First one.
The first can't, okay. So underneath the first one, I'll go 0 with a line through. So how many choices do I have for the first one then? 9. Any restrictions on the next blank? No. How many choices do I have then? How many choices do I have then? Because it doesn't say that I'm not allowed to repeat, right? Followed by? Okay. 2 letters. Which are, sorry, what? So how many choices do I have for the first letter? 26, because we're starting over. But once I picked a letter, how many choices do I have for the second letter since I'm not allowed to repeat now? 25. Mr. Dueck, why didn't you use the Scrabble bag? For letters of the alphabet, 26 letters is a bit much to draw. For digits, for numbers, for small amounts, I use the Scrabble bag. What's 24 times 9 times 10 times 10 times 26 times 25? How many different license plates can this country have before it has to go to a new system? And again, we're already well past trying to count these on our fingers. There's no way if we tried to make a tree or a list that we could track all this. What do you get?
1,400,000.
Read me the digits. 1, 4.
No. It's
Nope.
actually 14,040,000.
1, 4,
0,
0,
4,
4. How many zeros? 14,040,000. I would defy you to make a tree and list them all. That's not going to happen. Okay? Before we turn the page, what are car license plates in BC? In BC, we have, okay, we have letter, 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 number, number, number. Are we allowed to repeat? I know, I'm getting there. Are we allowed to repeat? Yeah. So it's 26, 26, 26, 10, 10, 10. Can you multiply that? How many do we have? I know. This is what license plates were until about 8 years ago. It was 3 letters followed by 3 numbers. How many?
17,570,000.
And we ran out. So what was the quick, easy way that we were able to double the number of license plates? That's not for cars. No, I'm talking cars. Don't change the question.
Number, 2 letters.
No. Yours is...
Mine is the new one. It's got a letter, 2...
Oh, are they changing? Okay, because about 10 years ago, they went number, 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 letter, 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 which just doubles it. But now you're telling me they've run out again? And so now they're mixing and matching. It's still 6 characters. Okay, so if it's 6 characters, how many choices do I have for the first blank? It's 36, 36, 30. You know what? It's going to be 36 to the 6th power, right? On your calculator, how many license plates are we good for before we got a problem? What is 36 to the 6th?
2,176,782,000.
We're probably okay. Probably okay.
At least for a couple more years.
Okay? And you laugh, but time and time again, we have misestimated. If you don't believe me, IP addresses, which IP version 4 was thought to last to 2050. It ran out 2 years ago. They skipped IP version 5. They went to IP version 6, which just adds extra characters. And they're hoping that'll work because that, I think, is in the trillions. What they didn't anticipate was every one of your mobile devices has its own IP address. That flooded the market very quickly. Okay? So we miscount all the time. In Ontario, their license plates have 7 characters. They're really hedging their bets. You'll notice, though, in the Yukon, I think their license plates, or in Northwest Territories, have 5. They're probably safe for a while. 3. Okay? But you can see why. They don't need more. What are we going to run into a problem with in your generation? Don't think license plates. What else do you have that's part of your identity?
Social insurance.
No, even more basic than that. Phone numbers. We never expected that every one of you would have your own phone number. When we set up the phone number system, we figured, oh, every 4 or 5 people will share a number because families, right? They set up the phone system about 75, 80 years ago, and they went, okay, 3 digits, 4 digits, that'll be plenty. The 3 digits will be what town you're from, and then the 4 digits will identify what home you're in. Well, that ran out about 15 years ago. We had to add the area code. Well, we already had the area code, but it was just kind of an afterthought. We made it mandatory. So now you had to dial an area. I'm telling you, by the time you guys pass on, I'm sure we'll have to add either extra digits or another 3-digit prefix, or we're going to run out. Because probably by the time you guys are into your adulthood, every human being on the planet, except for kids under the age of 10, will have their own individual phone number. Oh, wait a minute, no. A lot of people will have 3 or 4. One for business, one for or whatever. Yeah.
What about the idea of recycling license plates and phone number?
The problem is you can only recycle a license plate or a phone number if you absolutely know with conviction it's out of circulation. Far too many license plates are sitting in junkyards gathering dust, but the motor vehicle branch does not know officially that they're out of circulation. For all they know, a thief could have stolen it and be waiting to use it to commit a crime. So they can't put it back into circulation. Right? I mean, you know, maybe not think of it, but they have to think of those things. Turn the page. So some ways that simple fundamental counting principle affects you folks. But by the way, why were originally phone numbers 7 digits long? Numerous studies have shown that you have 2 different types of memory. You have what's called long-term memory. What's long-term memory? All of you know your birthdays. That's in your long-term memory. All of you know your address. That's in your long-term memory. And then there's short-term memory. Are you ready? Listen close, and I want you to pay attention. 5, 12, 20. Remember that. Short-term memory is where you stored that. Because if I ask you that a year from now, what were the numbers?
5, 12, 20.
But a year from now, that will be there. Okay? It turns out short-term memory can hold, on average, take a guess how many separate things? A phone number. Okay? Because that's one of the most common things before cell phones that we put in our short-term phone memory. Can you tell me the phone number for the store? And your husband or wife would rattle it off and you would dial it from your short-term memory, but 2 weeks later you wouldn't have it in your brain anymore. It was stored in your short-term memory. Many studies have shown 8 or 9 characters, 8 or 9 separate things, very difficult to store in your short-term memory. Not everybody, some have better, some have worse, but on average. Nothing to do with math, but if you haven't figured it out, nerd trivia. Example 5. With a bit of cleverness, did I hear a phone go off?
Yeah. It was Rachel.
It was Carm. I know. So,
Round of applause for that one.
you know what? That'll work great on Monday, last block, when we come back from our long weekend. Now, my Block A physics kids are going, this is great because I had one go off in Block A physics. So they're going to be getting Timbits first block in the morning, and they're going to be getting Timbits last block of the day. Who's in both? Look at you guys. Just a sugar rush. Karn, we always start out in the fundamental counting principle doing questions with scrambled letters as words, because it turns out with a bit of cleverness, you can transform a question into numbers or words. Pathways. There are 2 routes from Pitland to Queensville, 3 routes from Queensville to St. Luke's, 3 routes from Pitland to Rutherford, and 1 route from Rutherford to St. Luke's. Pathway problems. How many ways are there to get from P to S going through Q? How many choices do you see? No. How many not how many steps. How many different choices, how many different stations, how many different waypoints do you see? to go from here to here, a total of 2 choices. I can go P to Q. How many choices do I have?
2.
And I can go from Q to S. How many choices do I have? If I want to get to St. Luke's and I'm going through Queensville, how many choices do I have? Grand total. How many ways are there to go from P to S through Q? 6. Now I got another option. Instead of going through the top path, I could go through the bottom path, through R. How many ways are there to go from P to R? How many ways are there to go from R to S? How many ways are there to go from P to S as long as I go through R? Now here's the million-dollar question. If I don't care which way you go, how many different ways are there? And I'm going to tell you the answer is not 18. Listen closely. To go from P to S, I can go through Q or R. And means multiply in combinatorics. Do you know what the word or means in combinatorics? Addition. And so as we're adding to our skills, and I'm going to be flogging this to death, and means multiply, or means add. Or means add. That's also going to be important in probability. If you want to figure out the odds of, suppose you're picking 2 cards, and you want to figure out the probability that the first card is a heart and the second card is a diamond, you're going to multiply those. If you want to figure out the probability that the first card is a heart or the second card is a diamond, you're going to be doing some adding. Trust me. Or means add, and means multiply. So it says here, in part C, we could travel from P to S via Q. Here's the key word, or from P to S via R. And or means add. Or means add. A few more and we're done. Telephone numbers. Okay. The telephone numbers allocated to subscribers in a rural area consist of one of the following. The digits 3, 4, 5, followed by any 3 further digits, or the digit 2, followed by one of the digits 1 to 5, followed by any 3 further digits. How many different phone numbers are possible? Which word did I emphasize? You know what I would do right now? I would say there's going to be a big plus sign in my equation. You know why, Chelsea? Because or means add. I'm going to figure out the first one on the left, I'll figure out the second line on the right, and then I'll add them together. So the first one, what does it say? It says first we have to have the digits 3, 4, 5. Do I have any choice, or do I have to have the digits 3, 4, 5? What does the question say? So this sounds strange. How many ways do I have to choose the digits 3, 4, 5 if I have to have the digits 3, 4, 5? Well, only one. Not 3, only one. I said I have to have that. Only one way to choose that because it has to be there. And what else? 3 blanks. Any restrictions on those? No? So how many choices do I have for the first blank? How many for the second blank? How many for the third blank? 10. Or the digit 2, do I have to have a 2 there? Yeah? How many choices do I have for the 2? So leave it 1. Followed by one of the digits from 1 to 5. How many choices do I have for that blank then? 5. Followed by any 3 further digits. Can you see the equation? By the way, if you're multiplying by 1, does that make a difference at all? So Sterling, if you don't want to put the 1 times, you can certainly skip that. But it's going to be 1 times 10 times 10 times 10 plus 1 times 5 times 10 times 10. You know, I think I do this in my head because 10 cubed is 1,000. So the answer is 6,000? Double check me. Yeah? It's 5,000 plus 1,000. It's 6,000. Not that impressive to do that in my head. All right. Let's put it all together. Suppose you want to figure out the number of distinguishable, different 4-letter arrangements. Can you underline the word 4-letter arrangements? So we're going to be drawing 4 blanks. That can be formed from the word what?
English.
Those are my letters. How many letters in the word English? This is where I'm going to use my Scrabble bag. In fact, over on the left here, I'm going to go E, N, G, L, I, S, H, and I'll jumble them. And it says in brackets, note, there's an implication that each letter of in the word English occurs once and can't be repeated. In other words, I'm going to reach in and I'm going to pull out a letter from my Scrabble bag and I'm not going to put it back in. No repetitions is what we say. All right. It says, determine the number of distinguishable 4-letter arrangements that can be formed from the word English if A, no restrictions. How many letters are we pulling out grand total? How long? So you know what? 4 blanks. How many choices do I have when I first reach in? Okay, I picked a letter. How many choices do I now have? Okay, I picked another letter. How many Then? 4. Spot the pattern? Okay, if we have no restrictions and no conditions, from the word English, how many different unique 4-letter words can I form? 7 times 6 times 5 times 4. 7 times 6 is 42. 5 times 4 is 20. 840? Oscar, can you read B to me, please? Ding, 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 ding. Okay, we have a restriction. And you know what? I'm going to do something a bit strange. Can you all cross out the word first and replace it with the word last? Just to show you that the location of the restriction doesn't make a difference. I'm going to do it first no matter what. How many blanks am I going to draw? 4. Oscar, can you read to me the new modified condition? We're going to deal with it first. What does the last letter have to be? So underneath there, I'm going to draw a letter E to say that's my restriction. Look at my Scrabble bag. How many ways are there to pick an E? And I just picked it. Are there any other restrictions? Okay, how many ways are there to pick the first letter now? Not 7. How many? 6. I picked one. How many ways are there to pick the next letter now? I picked one. How many ways are there to pick the next letter now? Six times 5 times 4. 20 times 6, 120? If you've mucked up your Scrabble bag, you can quickly redraw it. I'm just going to erase that little slash. Or often I'll just reuse the Scrabble bag in different colors over. C. Mackenzie, can you read to me C, please? Okay, we're going to decide something for the rest of the year. The vowels are only going to be A, E, I, O, U. We're never going to include Y. And I know sometimes, but not for the counting. When I talk about a vowel, A, E, I, O, U, what's the complement of the set vowels? Consonants. Okay, but I also threw in some set notation review for you. Complement is the opposite. Okay, how many blanks am I going to draw? 1, 2, 3, 4. What's the restriction, Mackenzie? You know what? I'll go, how about vowel 1, vowel 2. Okay, the first letter has to be a vowel. How many choices do I have for that then? 2. Let's suppose the I went there. The last letter has to be a vowel. How many choices do I have? E. How many choices do I have now for the second letter? 5, then 4. 2 times 5, 40. Dope. Bring back the G. D. Tougher. Ben, what's the restriction for D?
The word must contain a G.
What that means is there has to be a G where, listen closely, in the first location or the second location or, I just saw Ty go, third location, or the fourth location. We could do this 4 separate times and add our answers. But I think if we're clever, we can actually turn this into a times, which is less work. So I'm going to do one example. How many blanks am I going to draw? 1, 2, 3, 4. Let's say there, because that's one possible example. How many choices do I have for the G? Then, 5, 6, Mr. Dueck? Good gosh. 5, then 4, then 3. Now that's if G is at the beginning.
Wait. There's 7 letters.
Good gosh, Dueck, count properly. 6, then 5, then 4. Is that right?
Yes.
Sheesh. I knew there was a 6 there somewhere. My brain was telling me something was wrong. Okay. I could repeat this with G in the second location, repeat this with G in the third location. Guys, you with me? Repeat this with G in the fourth location. Wait a minute. How many choices are there for the location for G? It can be in the front, there, there, there. You know what? I can actually just go times by the number of choices for location. I turned it into a fundamental counting principle. It's going to be one of them, 6 times 5 times 4, times 4 different ways to do it. 6 times 5 is 30. 480? So you can see, Oscar, we're still doing the fundamental counting principle, but it is possible to get way more complicated pretty easily. Pretty easily. Last one and we're done. I like this question, I like this question, I like this question.
Is this question going to be on the test?
Probably. Okay. It says, consider class example number 3, where Eric was asked to determine how many odd 4-digit numbers there are. As an extension to this assignment, Eric has been asked to determine how many even 4-digit numbers there are and how many even 4-digit numbers there are that have no repeated digits. Okay. The first one is easier. The last one is yucky, and you'll see why in a second. But the first one, how long are these numbers? How many digits?
4.
Okay, let's draw 4 blanks. 1, 2, 3, 4. What makes an even number an even number? 0, 2, 4, 6, or 8. How many choices do I have for that? Again, you'll notice, Ashley, I'm doing the restriction first, even though it appears last. I don't care. I always deal with it first. 5. Now, in part 1, has it said that I'm not allowed to reuse number? Has it said without repeating? Then you picked an even number, you put it back, shake it up. How many do I have to choose from for the first digit then? Sorry, how many?
9.
Why not 10? Oh, I still can't start with 0. So I got 9 there. Okay. Put it back in, shake it up. How many choices for the second one?
9. Oh, yeah.
Why 10? Because in this first one, we're allowed to reuse numbers, which means I'm resetting the Scrabble bag every time. Is that okay, Darian? Yeah. You zoning out on me? Sorry? No. That makes it even, right? If it ends in an even number, it's an even number. Who cares about the original stuff? Oh, how many choices for my third? 10. 100. You know what? By the way, does it make sense that we got the same answer as the odd numbers? I think there would be the same number of even numbers as odd numbers. In fact, how many 4-digit numbers are there? 9,000. I just add them together. B. Even 4-digit Julia without repeating. Here's why this is tougher. Put your pencil down. Look up. You see, normally I would do this. I would say, okay, and I would say 0, 2, 4, 6, 8. That's a restriction. But also, what can't I start with? See, the problem is 0 appears in 2 restrictions. If I don't pick a 0 for the last number, then I have 9 that can go there, because I still can't start with 0. But if I do pick a 0 for the last number, well, that's going to, well, then I got 9 again, because I've already used up the 0. It can't start with a 0. The fact that 0 appears in both restrictions, unfortunately, means I have to break it up into 2 parts. I have to do, write this down, ends in 0 or ends in 2, 4, 6, 8. Who do we appreciate? It's going to make a difference because 0 appears in 2 restrictions. I have to look at the separate cases. The first situation, it ends in 0. How many ways are there to pick a 0 from my Scrabble bag? Okay, I just did. And I'm not putting it back in. How many numbers are left in my Scrabble bag then? 9. Can I put 9 here? Yeah, because the 0's gone. I can start with any of them. I picked one. How many numbers are left in my Scrabble bag now? For the second digit. Then, that's how many ways the even number can end in 0 and not repeat. What does or mean? Or. It can end in a 2, a 4, a 6, and an 8. How many choices do I have for that? 4. So it was one of those, let's say a 6. How many numbers are left in the bag? 9. How many of them can I use? Because there's still a 0 in there. Okay, I picked a 7. How many numbers are left in the bag? 8. How many can I use? All 8. I pick another one. How many numbers are left in the bag? This is a tough question. Anytime a restriction appears in, anytime one of your Scrabble tiles appears in more than one restriction, you better break it down into the separate cases and turn it into an OR question. What is 9 times 8 times, well, 9 times 8 is 72 times 7 is going to be 504, I think. I better double check. 9 times 8 times 7, it's 504. Or 8 times 8 times 7 times 4, 1,792. 2,296. What's your homework? I'm going to give you the homework from this on Monday. What I'm going to give you, I was trying to give you 20 minutes. I'm going to give you about 19. I have a take-home quiz for you, and I think you'll get it done in class. That's due first thing Monday. That's going to be some of the stuff you're going to see on your test.